both said the same thing. Let me draw, and it's always easier, of course, to draw this than to say it in words. But generically, we see something like this. Okay? Now, we're not going to need to go into this in great detail, but you can imagine how this arises. First off, if you're really far apart, there's no force. As you come closer together, think about what we know about atomic structure. We've got a positive nucleus, very dense, and then at much larger distance scales, often by 5 orders of magnitude, we've got some diffuse cloud of negative stuff, electron distribution, effectively. And so if you think about the interplay of those positive and negative charges in the two atoms, it's slightly complicated. But the end result is indeed this. So I get closer together, and there's some sort of overlapping at an appropriate scale between the electron orbit clouds of one atom and those of the other. And that manifests itself as we approach, as they approach each other, initially with some attractive force. But then, of course, you can imagine and think about this in terms of a mental picture of these two atoms with the image that I've described. Think about what happens when they get much, much, much closer. So in the sense that both positive nuclei are within the sort of radius of the electron orbits, then you might expect that you're going to get repulsive behavior, and indeed you do. Okay? So this is a strongly repulsive force, at very small separations and somewhat larger separations. It's attractive, and then as we go all the way up, it goes to zero as we expect. So this is the generic behavior of forces between identical atoms. And so we can kind of use this to inform a little bit what our modified ideal gas equation looks like. There's no way you would necessarily come up with this, and in fact it's indeed somewhat empirical. So we end up with a modified gas equation, most commonly associated with van der Waals. That's a name you know a lot from chemistry. And I'm just going to write this down. We're not going to use it much. We're mostly going to concentrate on the ideal gas simple world. But I just wanted to show you that this can be parameterized to take account of the real interactions between and size of molecules. And so this is a slightly more realistic gas equation. So this one was ideal. This is van der Waals, which I'm not sure I'm spelling correctly, but fine. What you see on the right side is exactly the same, okay? nRT. And then what you see on the left side is a modification of the pressure and volume terms. These are just constants, and it doesn't matter what they are, okay? So it's basically, again, empirically absorbing the fact that there are interactions and the fact that there's some finite size to the constituent. Is it obvious that it would take that form? I don't think so, okay? It's not obviously wrong, but, and obviously dimensionally it's correct, but is it obvious that you can parameterize this way? No, I don't think so. But this turns out to be a good approximation for less ideal gases. Yeah?
Are A and B dependent on the type of gas? Or?
Absolutely. Yeah. Yeah.
Do we have to know for the ideal gas equation at like what boundaries for pressure and temperature it breaks down? Because isn't there something like
you
that?
don't need to know that. Any problem I'm going to give you will simply, almost always it's going to be ideal gas problems.
Okay.
I might once in a while just give you a one-off problem that is specifically making use of this, but I'm never going to ask you about, can you tell me what range of validity this is okay, and so don't worry about that.
Another question is with the like diagram of force versus radius. I've seen something similar in chemistry except energy versus radius.
Okay.
Can you relate them using like F equals negative du over
You
dx?
certainly can, yes.
Okay.
I encourage you to go through that exercise and see what it looks like. In fact, I think there might even be a sketch in your textbook, but I'm not sure. But yes, absolutely. So you can look at it either on a force basis or a potential energy basis. Nice comment. Yep. Okay, so let me just quickly wrap up on a few last things on macroscopic, and then we're going to turn our attention for the remainder of the morning to microscopic. As soon as we get some more realism here, and we mentioned this when we started to define the Kelvin temperature scale, we know that we're not going to have our, let's say, ideal, or less than ideal gas remain in the gas phase all the time. And so as we typically cool it, maybe increase the pressure, reduce the volume, these effects are going to become more important. Think about that. Cool it, increase the pressure, lower the volume, these effects are likely to become more important. Why? Constituents are, as we're about to see, moving more slowly. They are also closer together. So the extent to which any interactions are important is it's going to start to appear more dominant as we do those things to our gas. So that means, of course, that we will start to eventually undergo phase transitions, and all of this leads to the idea of phase or state diagrams. And we're not going to do much with them right now, but I just want to show you a few examples, just so you're starting to become familiar with what they might look like. So, with real physical interactions between the constituents, we are going to find phase changes, and basically, generically, I'm just going to call this that the gas condenses. Condenses, I mean it can be either a liquid or solid phase, okay? So this slide leads us, as I said, to the idea of phase diagrams. And so let me show you a few examples of these. Let's see if I can start with a simplish one. Well, let me start off with a less simple one. Let's see how this works. Okay, very small, that's no good. Let me try something else. Maybe this one. Somewhat better. Okay, let me just lower the light level. What are we talking about when we talk about a phase or a state diagram? So again, we're still working in macroscopic variables, pressure, volume, and temperature. And so what we may be interested in doing is displaying the behavior of whatever chunk of material we have as a function of these three macroscopic parameters. Okay? So this looks pretty complicated, and in general it will be complicated for most materials. But what you can generically see is, first off, what have we got on the vertical axis on the left, pressure, on the horizontal axis, kind of in that left corner, volume, and then temperature going off in the third orthogonal direction. But roughly speaking, as you would expect, at high temperature, so on the right side of this image, the constituents, as we're about to derive, have a lot of kinetic energy. They're moving quickly. This is going to correspond, generally speaking, to the gas phase of a material. And then as we lower the temperature, you can see this condensation start to kick in somewhat complicated ways, depending on the interactions in the material. But broadly speaking, you see liquid and solid phases on the left side, particularly at low temperature. And then, of course, there's a dependence explicitly on pressure and volume separately as well. So it's a complicated diagram. More often than not, we might try and extract important information from these phase diagrams by projecting that information on pairs of variables. So obviously we've got three macroscopic variables. We can pair them up in three different ways. And so very often you'll see this projected onto those planes. Let me see if I can quickly show you an example of that, because it might be slightly more familiar to you. That's what I was attempting to show there, but that's way too complicated. Let's try this one. That's way too complicated too. Okay, we don't need to worry about the details, but let me just sort of, again, just give you an example. In this case, we've done it on the pressure versus temperature plane. So the volume is integrated over in some sense. And so you can see various different phases here. Turns out life's much more complicated than we've let on, not surprisingly, because atoms are much more interesting than we assume. But you can start to see some different phases, and most maybe interestingly, you can see some colored lines on here that correspond to phase transitions. So the things we talked about last time, yep, in terms of latent heats, that corresponds to those phase transitions. So you can see it's pretty complicated. We'll come back to some extent to these phase diagrams. We're not going to use them a huge amount, but I just wanted you to see some examples of them to get a sense of what, with real interacting constituents, we might expect in terms of the behaviors. All right. So, yeah.
On the other graph, was the only thing dependent on the volume, the gaseous state, or like the vapor state, like liquid, like solid, or the volume seems to only affect one specific part of the graph, the atom one.
It's a little hard to parse this, but there is some volume dependence. And the one I originally wanted to show you here was something like this, with the projections on each of the 3 pairs of axes. It is more complicated than that. And if you were to look, I guess this is the only pointer I have right here, there is some very specific volume dependence on the left-hand side here. So as you might expect, if you're taking something and you're compressing it, you're compressing it, you're compressing it, eventually you're expecting it to be in some condensed phase. Most often it's liquid first and then solid. So there is some action on the left-hand side of this. And if I could find quickly one that shows a PV, for example, projection, you would see that. Okay? So I encourage you to poke around a little bit on this if you like online, just to sort of become a little bit more familiar with these phase diagrams. 3 words of jargon, and then we're going to turn our attention to the kinetic model of ideal gases. So I need you to know 3 words of jargon associated with these phase diagrams. So, 2 of them I bet you all know, 3rd maybe not. Quiz. Isothermal, what does that mean?
Same temperature.
Same temperature, so T is constant. Isobaric.
Same pressure.
Okay, what's our 3rd variable? T is constant. You want to know the jargon for this?
Isochloric.
Isochloric, okay. I'm not sure how many of you would have heard that. That one we use less. We use less in common conversation. Okay, so all you need to know is these words mean those things, okay? I'm not going to say any more about it. Any quick questions on any of this stuff before we turn our attention to the microscopic picture? Okay, all right, so from a physicist's perspective, this is all well and good, sort of historical more than anything. We've learned some things, fundamental things, but to be honest, it might all seem slightly, I don't know, well, it's empirical for sure. We haven't really gleaned any understanding of what's going on in terms of the actual underlying mechanics and so on and so forth. So physicists are much more interested typically in what we're about to do, which is the sort of kinetic theory approach to understanding this stuff. Okay, so no big surprise what we're going to do, because I've tried to inform the last couple of sessions throughout with the idea that, of course, we've got these moving microscopic constituents, atoms, molecules, moving around, somewhat non-interacting, depending on how realistic we want to be. But what I want you to think of as informing what we're about to do is a volume of gas as being essentially Non-interacting, meaning purely elastic collisions. So that's it. There's nothing other than transfer of momentum in those elastic collisions. Non-interacting point-like constituents, atoms, let's say. So we're going to take a look at this idea. Imagine we've got a volume filled with point-like non-interacting constituents. They're bouncing around, bouncing off each other, bouncing off the walls. See what we can learn about this simply by applying Newton's laws, essentially, as those constituents collide with the walls of the container. And it turns out we can get some surprisingly useful and even correct information out of this. So, kinetic theory. I debated before coming down whether to go through this in detail or not. It's a little bit of a lengthy thing. I thought maybe I should just ask you to read through it yourself, but I kind of feel it's sufficiently fundamental that it's worth going over in class, so I'm going to do it. All right, so let's go ahead. Kind of gives it away. It's going to be a lot to do with the kinetic energy or motion of the constituents. Okay? So, what we expect in general for macroscopic volumes of gas, obviously have very large numbers of constituents. By which I mean at least probably an order of Avogadro's constant. Okay? If you take a gas at standard temperature and pressure, so maybe I constructed a liter volume of air in this room, it contains of order Avogadro's number of constituents. Okay, so we're talking about very large numbers. So that obviously suggests that some ideas from statistics might be interesting. So statistical parameters are important. And we're going to do some averaging. So statistical parameters are important. So, we've got macroscopic volumes, we've got very large number. There's one thing. We're assuming again dilute, so we've got widely spaced constituents. And we've basically got elastic collisions of those constituents, both with each other and with the walls. Okay. So, let's see where this gets us. I'm going to start off down here. So we've got a cubic volume of gas. Maybe I'll draw it down here. So I'm simply going to set up a cube in a three-dimensional Cartesian coordinate system. So if I can draw this quickly. Okay, so y, x, and z. Okay, so that's what's hidden, making up our cube. And this cube has a length, a side of length L, so it's an L by L by L cube. Okay? So volume is simply L cubed. And I'm going to look to begin with at a single molecule or atom inside here. Let's say it has an intrinsic mass m, and it's moving in some random direction with a speed v. Okay? So here's obviously the microscopic perspective. Okay, so that's what I want you to be thinking about. Let's say I have n moles of gas, has temperature T in Kelvin, most naturally, and we've got a molecule, just one for now, of mass m and velocity v. All right. Okay, so what's our goal here? We want to somehow relate the pressure of the gas to the speed of the constituent molecules. So it's not a difficult thing, it just requires a few steps. Just let me get a sense of, from you, how you imagine these things are related. It's not difficult, but I just want to get a sense of your mental picture of this before we actually derive it. So I've given you this cubic volume of gas. It's got a lot of constituent molecules in it. They're moving around with a certain speed. What's our path towards understanding something about the pressure inherent with this volume of gas? What are the things we want to be thinking about?
Something with pressure seems how much, I don't know, it's like how much the molecules are pushing onto the
Sure.
wall, and we can use how much those are pushing against the wall, and then we can in the future relate to the kinetic energy to temperature.
Yeah, that seems pretty good to me. So just imagine this sort of seething volume of gas molecules. They're all bouncing around at a certain speed. As they hit the containers of this volume, of course, they hit them, and if they're elastic collisions, they bounce off. We're going to analyze that very simply in just a moment. There's some momentum impulse as they bounce off the walls, okay? You average this over zillions and zillions of molecules. It corresponds to a net force. Force divided by area gives it the pressure. And as you might imagine, the faster they're moving, the more of an impulse they impart, therefore the pressure is bigger. So that's basically what we're going to derive with a few lines of derivation, I guess. All right, so there's the setup. And I'm not quite sure best to do this with the chalkboard configuration here. Let's try something new. The only reason I'm doing this is because there are a fair amount to keep track of, and it would be nice to see all of it at the same time. Okay, at the moment I'm going to raise this back up so that you can see it. All right, so we're going to start off with Newton's law. Colliding with a wall. Okay, so first off, we need to figure out the force associated with the elastic collision of one molecule with one of the walls. We'll maybe take the wall on the right-hand side. All right, first off, when I look at the right-hand side here, I'm just going to take one side of the cube. The area of this is L squared, that's obvious. Now I'm going to take, I should add some color maybe. Let's look at this right-hand wall here. My molecule is in the middle of this cube and it's moving like this. What I care about is its velocity in the horizontal or x direction. We'll see why that's important in just a moment. If this molecule collides with the right-hand wall, so it's an elastic collision. What can we say about this? There is a change of momentum of the molecule in the x direction. So let me write this down and then we'll make sure you're okay with it. So as usual, just delta momentum is the final momentum minus the initial momentum. And we're looking at the change of momentum in the x direction, so I just need the x component. So think about this. Elastic collision of some billiard ball, something like this, has an x component, Vx. So it collides, and its x momentum is inverted, bounces off, so it's headed back this way. What about its momentum in the y and z directions? Any change? No, right? Okay, so I only care about the change in momentum in the x direction, and it's this. So this is the change in momentum that the molecule experiences. Newton's laws, third law in this case. I can say that the momentum kick that the wall experiences, still in the x direction, is equal in magnitude but opposite in sign. Okay? So the molecule bounces off, it has this, has its change in momentum. I impart this momentum to the wall, it's in the other direction. So that's the first thing. Okay, now this thing's in motion. So imagine our molecule rattling back and forth. So bouncing back and forth. And what's the time between collisions with the right wall? So we try and write this down. Time between collisions with the right wall. Let me call this delta t. And in terms of the length of the box or the size of the box, I can simply write it like this. Okay? So in the x direction, there's a speed vx. These are elastic collisions. There's no changes. It's just rattling back and forwards. It's got to travel a distance 2L, go one way and come back. That's the distance, that's the velocity. This is the time it takes to bounce, for it to bounce back and forth between two impacts on the right-hand wall. So the rate of momentum being imparted to the wall slow, but it's kind of worth knowing the details. In the end, we're pretty much only going to use the result. Hopefully this is correct, and this is for one molecule. Okay, let me raise this up. Make sure you're okay with this. All right, so now I've taken time to go back and forth between two successive bounces on the right side. I've done a little bit of manipulation by taking the momentum imparted for each collision and figured out what the rate of momentum is, knowing what the associated time interval between collisions is, and I get this expression, mvx squared over L for a single molecule. So that's an important first step. Now we want to look at many molecules. Total force and so let's say for capital N molecules. Okay, now in principle each of these might have a different velocity. We'll worry about that in just a moment. So the total force can say is dp by dt. Okay, so I could, taking this simple derivation over here, write this as mvx1 squared over L plus mvx2 squared over L plus mvxn squared over L. Okay, make sure you're okay with that. So force really dp by dt, our usual definition from last semester. I'm just doing this for n different molecules, each of which in principle has a different velocity at any instant. So it's a simple summation. And now we're going to take advantage of some statistical properties of this ensemble. Before we do that, let me just simplify this to see if we can figure out what the pressure is. So the pressure ought to be the total force divided by the area. So cleaning things up a little bit, bringing